Hello, my name is Markantonatou Vasiliki. I'm a marine ecologist working on systematic conservation planning at the Aristotle University in Greece. Coastal and marine ecosystems are among the most productive areas with significant benefits to social and economic prosperity of human societies. Moreover, coastal zones are vulnerable to human activities occurring at sea and/or at land, climate change and extreme weather events such as flooding, erosion and sea level rise. Demands for marine space for the development of human activities and the exploitation of resources are increasing, and we are facing a rapid biodiversity loss. Many European initiatives and directives have highlighted that there are interactions between marine and terrestrial environments and that should not be neglected. These directives highlight the need for the development and implementation of an integrated planning approach that accounts for both realms and their connections if we really want to effectively protect biodiversity. Systematic conservation planning is a quantitative approach for spatially identifying priority areas for conservation. It sets explicit conservation targets on ecological features and succeeds them with the least implementation cost for users. To succeed these targets, it uses statistical methods, models or algorithms to identify the priority areas or reserve networks. It is therefore a transparent and robust process that is based on an ecosystem-based approach and provides cost-efficient solutions to managers and decision makers. The identification of reserve networks is based on specific principles. First of all, we should ensure that local biodiversity of an area should be conserved at all levels of organization, meaning at the population, species, community, and ecosystem level. Therefore, efficient conservation means to conserve also important stages of a species life cycle and related habitats, such as spawning and feeding grounds, nurseries and migratory corridors, are required. We should also protect all the relevant environmental parameters that support the survival of a species, such as geomorphological structures or other abiotic parameters. Adequacy supports that biodiversity should be maintained at a reasonable level to secure that the maintenance of the ecological viability and integrity of populations is sustained. In reality, this principle asks to identify how much is enough to protect in order to ensure that populations, species and communities are adequately protected. We address this by setting explicit numerical targets on the ecological features that we want to protect. Each area has an ecological value depending on the features present and their importance to be protected. Areas with unique features such as rare and threatened species are considered of high ecological value, and therefore these areas are considered unique and irreplaceable. We also recognize that existing management measures like the established protected areas already protect to some extent biodiversity, and the additional priority areas we propose will complement them by contributing to unrepresented features. Systematic conservation planning is a structured, dynamic and transparent process with the capacity to involve stakeholders from the beginning. The process is characterized by clear steps that are quite straightforward. First, we define the boundaries of the planning area and set the general planning goals. Then, we define the planning units, which are the smallest spatial area that you suggest for management actions to be implemented. Planning units may be of various sizes and shapes, depending on the concept and the needs of the analysis. Then we collect spatial information with the ecological features present in our study area that we want to protect. For these ecological features, explicit numerical conservation targets are set. For instance, protect 10% of Posidonia oceanica habitat or 20% of a species distribution. You also map the socioeconomic information or the cost layer that expresses the foregone revenue of actions implementation. For instance, how much will be the loss for fishers if you prohibit fishing in an area because you establish a reserve? Cost may also express other types of monetary values that we will see later, but in any case, cost should be expressed ideally in financial terms in order to reveal the trade-offs between conservation and socio-economic impacts of management actions. However, this information is difficult to find. Analysis is performed with decision support tools that provide a spatial configuration design of priority areas or reserve networks. To have a successful and realistic reserve network plan, the various conservation objectives for the ecological features are simultaneously reached with the least possible annoyance or cost for users. For instance, popular fishing grounds that provide important income for fishermen will be avoided to be established as reserves, as this action will have a major impact for fishers. Similarly, on land, we would avoid to establish a reserve at an agriculture area that a great proportion of the local community depends on for their food and income. This approach not only makes conservation solutions more realistic and applicable, but also helps to mitigate stakeholder conflicts and inequalities. The most commonly applied tools for this type of analysis are Marksan and Marksan with Zones software, developed by the University of Queensland in Australia. Interactions between land and sea are crucial to be accounted in conservation planning if we want to fully protect vulnerable species that their long-term sustainability depends on the protection of areas in both realms. For instance, migrating birds that live and breed on land but use the sea for feeding, or sea turtles that live at the sea but lay their eggs on the beaches. However, until now, conservation planning in terrestrial and marine realms has largely proceeded neglecting this interconnectivity between realms and faces them as if they were unconnected. Some attempts for land-sea integration have failed to address these fundamental concepts of systematic conservation planning. This is due to the complexity of processes that link the terrestrial and marine realms that are often highly asymmetrical, complex, and occurring at various scales. There is also uncertainty due to our limited understanding for these processes' dynamics in time and space, particularly considering climate change. There is limited spatial information to represent these interactions available, as these processes are difficult to define and monitor. Another issue is that one activity operating in one realm may impact another realm, and the source can be many kilometers away from our planning area boundaries. Therefore, integrated land-sea planning requires a much more complex process in contrast to the single realm planning. In integrated land-sea planning, the setting of the planning domain means that we identify the sources and zones of influence of cross-system threats and the spatial representations of land-sea processes. Defining the planning boundaries is not always straightforward. For instance, the terrestrial part that influences marine areas can extend far inland. In these cases, protecting a species at the sea means that you have to apply mitigation actions on land. Stakeholders must be identified and involved from the beginning, taking into account that there is diversity of actors in terms of various interests, jurisdictions, and backgrounds in both marine and terrestrial realms. General goals should target individual realms, for example, the protection of terrestrial and marine species and habitats, the maintenance and restoration of the ecological processes between the various realms, for instance, the nutrient flows or the movement of organisms. Goals should also target the mitigation of cross-system threats, targeting potential sources of detrimental flows in one realm that impact species in another realm, such as pollutant discharges. Cross-realm connections in any region will be numerous, but discussions with stakeholders can help to identify the most relevant and those for which there are spatial data. In any case, conservation goals are initially framed qualitatively and are later translated into quantitative targets, preferably with stakeholders' participation. Spatial ecological information may refer to species patterns and ecological processes across the land-sea continuum. We usually use information that is related to species and habitats distribution. This information may be predicted through models or may be found in relevant databases, compilation of sampling information, or expert judgment. Models usually provide information in single or separate realms in the case of multi-realm species. However, the type of information and resolution may vary greatly. The ecological processes that link the land and the sea are defined by natural flows of water, nutrients and energy, or the movement of organisms between and within realms. These processes are critical for the persistence of biodiversity across realms, therefore should be protected. These processes can vary in nature, in time and space, and may have directions. So in the case of salmon's migration, that are anadromous fish moving from the sea to the rivers to spawn, there is a specific direction that actions should target. Other important components that should be integrated in land-sea planning are the values derived from ecosystems to human societies. Including processes or features linked with ecosystem services and determining the spatial alternatives for their protection or restoration is important. However, spatial representation of ecosystem services is not always easy, and frequently these features are generally overlooked. Future alternations caused by climate change are also important to integrate in planning. For instance, the erosion and sea level rise are crucial factors for evaluating which areas are more resilient to climate change in order to prioritize investment for protection. Vulnerable habitats are expected to be lost due to the increase of temperature, or important areas for some species' life cycles are expected to be displaced. For example, several studies have highlighted the alternation of sea turtles' migration corridors and the loss of some nesting beaches due to climate change impacts. Using climatic modeling, we can predict which areas are more resistant to climate change and put more emphasis for their protection in our planning strategy. Similarly, integration of cross-realm threats means that we need to identify the sources, the zones, the magnitude and the direction of impact, and of course the realms affected by these impacts. For instance, nutrient runoff from agriculture on land causes eutrophication, phytoplankton blooms, and hypoxia to coastal and marine ecosystems. Although most threats propagate from land to the sea through the rivers, there are also processes where land can be affected by marine threats. For instance, waves and tides transfer marine nutrients from the sea to the rivers, alter the geomorphology of estuaries, and cause erosion to the coastal zone. There are also threats that influence many realms simultaneously. For example, dams have two-direction effects, causing the alternation of terrestrial and marine ecosystems morphology and structure. The extent of threat influence can be mapped using catchment or diffusion models, or by creating buffer zones of various magnitude impacts around the source of threat. Ideally, integrated land-sea planning should integrate all the economic, political, social and ecological factors to select areas with higher long-term viability and avoid areas with high conservation costs. Cost represents the social and economic loss of communities when a management action is implemented. Costs may be land acquisition, restoration costs, management or mitigation action costs, transaction costs, or economic losses for users. However, these evaluations are much more complicated and multiple interests should be accounted ideally simultaneously in terrestrial and marine realms in comparison to single realm planning, which is generally an easier and simpler approach. Here we see an example of an attempt to integrate land and sea interactions using spatial prioritization approaches with Marxan software by Tallis et al. Marxan provides spatial solutions for establishing reserve networks in order to protect efficiently biodiversity with the minimum possible cost for resource users. Initially, Tallis et al. Selected more than 380 species and habitats in both terrestrial and marine realms to represent the local biodiversity in the Pacific Northwest coast and target their protection. They also mapped the main threats in land and sea that threaten these species targeted for protection. In the beginning, they ran a planning scenario where threats in both realms were dealt as if they were unconnected, an approach commonly applied in single realm planning. At a second step, they integrated the interaction of land and sea by propagating threats from land into the marine environment through the Columbian River. So they added the information that additional threats, apart from the activities operating in the sea, will enter the marine environment and cause degradation. The land-based nutrients and pollutants would run off in the sea through the river, creating a river plume that you see in red in Figure B in the marine realm. Configuration outputs from Marxan for the two scenarios showed a clear influence of prioritization when considering the interactions between the two realms. In the single realm system, Threats approach ignores completely the impact received from land and selects areas within the river plume that are in reality very impacted. On the contrary, cross-system threats approach accounts for the impacted area within the river plume and therefore avoids to identify it as an area of conservation importance. As you can see, the prioritized areas in this case are located away from the influence of detrimental flows from the river. So we conclude that integrated land-sea planning is an important component that should not be neglected. Ignoring the connecting processes between terrestrial and marine realms may increase the failure of conservation efforts targeting areas that are already highly impacted and may not provide an efficient conservation solution to guarantee the persistence of biodiversity in both realms. Although this is a challenging process with several difficulties, limited understanding, and lack of relevant data, systematic conservation planning should move towards this direction in order to efficiently inform decision-making.